In this lecture, let's talk a little bit more about the details of general relativity, and let's start with the space-time metric, but also move on to gravitational waves. So it turns out that the fundamental equation of general relativity, if I write it very compactly, is this. G mu nu is 8 pi g, where g is Newton's gravitational constant, over c to the fourth times t mu nu. Now, what is g mu nu? It is a tensor, you can think of it as a matrix, for the curvature of space-time. And t mu nu is the source, if you like. It's what's so-called stress energy tensor. Again, you can think of it as a matrix, which has the energy, mass, and momentum involved. And they are related by Newton's gravitation constant. Good, okay, some connection to gravity here, right, that we knew. And relativity, because you've got c to the fourth power in the denominator there. All right. Now, we won't work with the details of this equation, but basically that encodes, once we're able to write out what g mu nu and t mu nu are, we could decode and start to calculate, not that it's easy, within general relativity. But let's talk about the qualitative effect, which is mass and energy in Einstein's general relativity curve space-time. It's a geometrical effect. Now, without any mass or energy, we have flat space-time, and we've addressed that in special relativity actually already. And we can think of it that a Lorentz invariant space-time interval, ds squared, can be written as c dt squared, and then minus dx squared minus dy squared minus dz squared. That was our Lorentz invariant metric in four-dimensional space-time. Now, I've written it here also a little bit differently. I still have the c dt squared there. But if we write it in spherical coordinates, I have a dr squared and then r squared d theta squared plus sine squared theta d phi squared, all multiplied by r squared. So that's the flat space-time metric in spherical coordinates. Now, what happens if you do have some mass energy? For example, the universe. If we have a homogeneous and isotropic universe, that is, it is of the same mass density throughout and looks the same in all directions, general relativity predicts this metric. So it looks somewhat similar. I have the c dt squared in front, but then I have r, a function of time, r of t squared, times, in brackets then, dr squared over 1 minus k squared, and then this term we saw before, r squared d theta squared plus sine squared theta d phi squared. This is known as the Friedmann-Lemaitre Robertson-Walker metric. And the r of t that's out front of the spatial pieces here is an expansion or contraction term, right, depending on its, if it's growing or shrinking. And k is a constant, which can be either minus 1, 0, or 1. It has to do with the curvature of space-time. Okay, now, so those are just some details. We'll come back to that space-time metric. But another important, very important prediction of Einstein's equation is that it predicts gravitational waves. So very much like Maxwell's equations predicted electromagnetic waves, Einstein's equations predict gravitational waves. And we can see that there was a problem anyway, because Newton's law of gravitation essentially assumes that gravity acts instantaneously between two masses, even if those two objects are separated by light years. In other words, we can talk about the force between the sun and the earth, but it doesn't say anything about how long it takes that force to propagate from the sun to the earth, or from the sun to another galaxy. It happens instantaneously. It just depends on 1 over the distance squared, which doesn't agree with special relativity. Relativity tells us that nothing can travel faster than the speed of light. So there's some issue there. In fact, the light takes about 8 minutes to travel from the sun to Earth. So thankfully, general relativity can come to the rescue, and its equations can yield a wave equation, or do yield a wave equation, for the propagation of gravitational waves, which, because we just saw that, or at least I noted that general relativity is a geometrical theory. It's describing the curvature of space-time, that gravitational waves are propagating distortions in space and time itself. The speed of propagation of those waves is c, the speed of light in vacuum, just as it is for electromagnetic waves. However, unlike, say, electromagnetic waves, it is not a vector field with a polarization along one direction, like the electric field or magnetic field. It is a tensor field. So what that means is it oscillates both stretching and squeezing along two directions simultaneously. So the tensor field just means it's got kind of two components, if you like. And I can try to illustrate that graphically. So if I imagine this is some object, this crosshairs here, as a gravitational wave passes through your screen here, it can stretch out the object along one direction and compress it along the other. And then in the next oscillation, it can stretch it vertically and compress it horizontally. And it's going to alternate stretching and compressing along these two directions as a wave passes. That's what a gravitational wave will do. Kind of cool, right? But very hard to detect. So let me first, how do we know this prediction is validated? Well, the first real hint of that these gravitational waves must exist is indirect evidence for these waves. So we didn't detect the waves themselves, but we knew somehow energy was going somewhere. And the idea here was to look at a binary system, actually a binary neutron star system. And what these two physicists did, Hulse and Taylor, in 1974, was to measure the orbital period of this binary system. And for the results I'll show in a moment, got the Nobel Prize in 1993. So we're starting with a neutron star system here. And some neutron stars are so-called pulsars. That is, they emit electromagnetic radiation at rapid intervals corresponding to their rapid rotation rate. And so one of these neutron stars is a pulsar in this system, meaning it is emitting electromagnetic waves that can be detected on Earth. The other one might be, but it's just not pointing toward Earth, so we don't know about the other one. But that means we have a probe of what's going on with this binary system as they orbit each other. So such a binary system, as they rotate about each other, would be predicted to emit gravitational waves, just because they are orbiting, and general relativity would predict the emission of gravitational waves. So some energy is emitted in the form of waves from that system. As you emit the energy away from that system, then to conserve energy, the orbital distance between them must shrink. And as you shrink the distance, that's also going to decrease the orbital period. They're going to speed up in their orbit. Okay? So they might have been orbiting at one frequency, but they will speed up as they get closer and closer together. And so that period of rotation can be measured of this binary system, and was measured. It's been measured over actually decades now. And essentially, back at the time of Hulse and Taylor, their measurements of 75 microseconds per year change in the orbital period. So that's not a very large amount, 75 microseconds over the period of 1 year for this pulsar, this specific pulsar, PSR 1913 plus 16, was actually in very good agreement with general relativity. So it's indirect confirmation that indeed waves are being emitted, and that general relativity is correct in the prediction of those waves and the energy that would be emitted. And that's, of course, why it was Nobel worthy, right? Okay, so that's a measurement of indirectly that gravitational waves exist. Of course, the holy grail would be the direct detection of gravitational waves, that distortion of space-time itself. But gravity is the weakest of all the fundamental forces. So the direct detection of gravitational waves is challenging, to say the least. Unless you happen to be right next to a cataclysmic event. If you're next to where those neutron stars are, okay, then you can measure it. But we don't have one in our backyard, and maybe it's good we don't have black holes and neutron stars in our backyard. So you need both a massive source of waves, so the more massive the objects doing the waving, if you like, the better, particularly if they're colliding into each other, merging. And you need an extremely sensitive instrument, right? How sensitive? Well, first let's talk about the instruments that could do the measurement. So it turns out, over the years, the instrument of choice to measure distortions in space-time became the laser interferometer, very much like the Michelson interferometer that was used to invalidate the theory that there was an ether for waves, electromagnetic waves to propagate. So it's an interferometer that goes in two directions. And you need it in kilometer distance scales. Now, how weak are we talking about? Well, for known astrophysical sources, like colliding neutron stars, they spiral in and merge into each other, crash into each other, or merging binary black hole systems, one expects a distortion of space-time at the level of only 10 to the minus 18 meters at Earth, which is 1,000 times smaller than a nucleus. So we're talking extremely small distortions from these gravitational waves from, many, many light years away. Thousands, in fact. You can't really measure such a thing for individual nuclei one at a time. You need collectively a mirror which contains, let's say, of order a mole of nuclei, and look at the collective effects of that mirror. So it's extremely difficult. It's a very big engineering challenge. Nevertheless, such waves from a black hole merger actually were detected for the first time in 2015 by the LIGO and Virgo collaborations, which had these large laser interferometers. And for that detection, confirmation of gravitation, direct confirmation of gravitational waves from general relativity was culminated in yielding a Nobel Prize in 2017 to Rainer Weiss, Kip Thorne, and Barry Barish for their development and culmination of gravitational wave detection using laser interferometers. Now, one such of those interferometers is LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory. There are actually two sites in the US, one in Washington State in Hanford and one in Louisiana. But there's another collaboration known as Virgo that's in Italy, which also can make measurements. For the first discovery, actually LIGO had essentially the bulk of the data, and there was not much signal in Virgo, but that helped again in confirming this. The length of each arm for the case of LIGO is 4 kilometers in each direction, so it's enormous. And as I said before, we're looking for distortions of only 10 to the minus 18 meters. Now, since then, there have been multiple confirmations of colliding objects in accord with the general theory of relativity. And the most massive gravitational wave binary observed to date, meaning in the year 2020, by LIGO and Virgo is this one. It was 2 inspiraling black holes, that's what's been inferred, one of which had a mass of 85 solar masses and the other 66 solar masses. So quite a bit heavier than our sun, more massive than our sun. And they resulted in the formation of another black hole, a remnant, which had a mass of 142 solar masses. Now, you can probably do the math and see that 85 and 66 don't add up to 142. It's closer to 150. Where did the extra energy go, the mass energy? Well, it went into gravitational waves. And this is just an image, not an image, this is a simulation of what those waves would look like, I should say, as distortions, at least along 2 dimensions of space-time, from that gravitational wave energy emanating from the center there where the 2 black holes are inspiraling and crashing into each other. But anyway, this is the largest object that's been detected via gravitational waves. And in the next moment, I can animate this from the LIGO and Virgo collaboration teams, what this in spiral looks like and the waves that emanate out.